Hello guys, Sir DV here again to explain to you what the maximum and the minimum shear stresses is represented by the two-dimensional Mohr circle representation of a 3D physical state of stress. So let's consider here the figure of a continuum or a body, no? Upon which at certain point P on the surface, a vector sigma I represents the stress tensor, no? Upon which a normal vector n uh, is made to be directed, no, on the surface upon which P is located. So we now try to examine how the normal stress and the shear stress are related with the stress vector sigma I in relation to a two-dimensional Mohr circle representation. So the resultant force sigma 1 may be expressed, or sigma I may be expressed in terms of sigma n and tau, upon which by simple resultant equation, or what you call Pythagorean relations, we take note that tau squared plus sigma n squared is simply equal to the stress vector sigma I defined by a specific stress tensor. So take into consideration now uh, the principal stress as computed earlier analytically. We can therefore say that your the value of sigma I here is simply uh, equivalent, no, to another set of sigmas upon which a principal axis is oriented. Meaning to say that if you have a sigma I can make use of a sigma principal dot okay. So this is a simple expression of equivalence, no? Such that if we simplify this, this will simply be a squared term and another squared term here, involving the principal directions 1 or simply I. Okay, so this is true with the other principal stress and principal direction, and also true with the third principal stress and principal directions. So if I'm going to define now my normal component of your stress vector in terms of the Cauchy stress vector here, which is sigma j dot nj, I can come up with this equation here, no? In terms of, again, the same stress tensor, which is represented by the principal stress and the principal direction. So in short class, we're just trying to compare or make a relationship between the general stress tensor with that of this, the stresses oriented on the principal axis. So let's tag it as equation 2.10.1 and equation 2.10.2. And equation 2.10.3 is simply a simplification of equation 2.10.1, in which our tau was actually computed, no, by simply transposing the value of your sigma n square uh, at the right hand side. So let's use the Lagrangian technique by using a Lagrange multiplier lambda in order to maximize and minimize uh, the values of your direction so as to give us the maximum and minimum values of the uh, principal stresses, considering of course the normal and the tangential uh, components, which is the sigma n and the tau values. Okay, if I now use this Lagrangian equation uh, to form an expression upon which my tau squared here is simply substituted, and this um, expression here is actually the technique upon which the Lagrangian multiplier method was based upon. So we simply deduct it, no? Here, knowing that NI is simply an application of orthogonality conditions for directional vectors which are orthogonal to each other. Okay, upon substitution of equation 2.10.2 in the above equation for f, we simply get this, okay? So your sigma n here square is actually this term here below, okay? So this term here is simply the sigma n square. And taking the derivative of this function f with respect first to the first a normal vector n1, we will yield this result, no? So this is simply a derivative of the function with respect to the variable n1. So all of this does not have any n1 values will simply vanish. Okay, so this will become sigma 1 squared multiplied by 2n1. Okay, minus. So this is now uh, uh, in a quantity. So we still have to make use of the power formula. So 2 will be placed down there. So 2 times this quantity. So this quantity will stay as it is. And then we'll take the derivative of each and every expression inside the parenthesis that contains the n1 term. So we have here the 2 sigma 1 n1. And then we simply subtract, okay, this term here. The derivative of this term is simply a sigma times 2 n1, or equivalent to, lambda 2 n1, or equivalent to simply 2 lambda n1. Okay? So simplifying by taking out n1 there, and taking note that 2 is simply a factor that can be placed outside, and upon equating it to 0, the factor of 2 may be considered to be uh, insignificant. Okay, so this is simply n1, okay, factored n1. There's an n1 there and an n1 here. And then we simply retain the sigma 1 squared here, okay, the sigma 1 squared there, and then the minus 2 sigma 1 n1 squared here, plus this and plus this. And here what retains is simply the lambda there, no? So Again, as I've told you, the factor of 2 there simply is insignificant, since this next step we simply equated it to 0 to optimize the value of the stresses, so as to compute the directions later, the principal directions on the basis of a pure normal state of stress and a pure shear state of stress. So for the other derivatives, the procedure is just the same, no? So similar procedure will yield a very similar pattern, upon which N1 simply becomes N2 and N3 there. And the derivative, of course, will be with respect to N2 and N3 here. Okay. Also, the sigmas, the principal stresses, will change from 1, 2, and 3 there, and here from 1, 2, and 3 here. Okay. So uh, considering now the fourth equation, which is the orthogonality equation on the basis of this n1 squared plus n2 squared plus n3 squared equation, we now make use of a four equation, four unknowns, a four equation with three unknowns in n. Okay. Upon which, if we try to look, or if we try to interpret the values of n1, n2, and n3, this will yield direction cosines, which represents the principal uh, stresses, having two sets, no, of ni, yielding the minimum shear stress here and the maximum shear stress on the second. Okay. So for the first set of solution for n, yielding cosines, this corresponds to a value equal to an identity uh, matrix. Okay. So if you will take a look at this later on the Mohr circle, so it will be represented by a value of tau simply equal to 0, which means that it is lying on the sigma axis, exactly at the horizontal axis or the sigma axis. For the second set of solution for Ni, we simply set uh, any value, say n1 to 0. So this is the method we have done, no, in the previous problem, wherein there is some equations that are equivalent. So we need to make such assumption, no, in order for us to yield a third set of direction vector, no. So to solve now for the remaining values for n2 and n3, we will be obtaining so this kind of matrix of direction cosine, which is, if you will observe, are all the same, but only arranged in an order upon which your orthogonality property is satisfied. Okay, so we have to arrange it in such a way that if we take the that product of ni, so it will yield a value equal to 1, which represents the orthogonality conditions. And in this particular set of direction cosines, so your tau is actually equivalent to the maximum stress that can be obtained from the basis of these three equations. So these three equations will further be derived on the next presentation. And note that the values inside this matrix is a combination of a positive and negative values. No? So we don't restrict only positive values here. This can be a negative negative or a negative positive there, a negative negative or a negative positive here, or vice versa, and so on and so forth. So there are these possibilities simply gives you an indication that there can be more than three, okay, more than three representations of your principal directions on this regard. So for the Mohr circle as defined here, which is a two-dimensional representation of a 3D physical state of stress, so take note that what we have derived uh, here on this previous lecture serves as a justification or a reference for uh, the Mohr circle as presented here, okay? And if we are going to look at the tau max on the basis of the radius of these three circles, so we can say that here your circle 2 actually gives you the maximum value, since your sigma 1 and sigma 3 defines the diameter, the largest diameter upon which your tau max is obtained. Okay, of course, this circle 3 here has a smaller radius, and this circle 1 here has also a smaller radius than this circle 2. So I'd like you to take note of how these circles are constructed, no? Because we will be doing some graphical solutions later for us to visualize what the equations are, what the derived equations are really uh, as illustrated in the 2D representation of the Mohr circle. So this becomes now your sigma 1 minus sigma 2. Of course, there's an over 2 there, over 2 here, and this is the biggest radius, which is sigma 1 minus sigma 3 all over 2. So this is consistent if and only if sigma 1 is always greater than sigma 2 and sigma 2 is always greater than sigma 3. So if you are considering another uh, range of inequality, then uh, you must take note uh, how to capture, okay, numerically the maximum. So here if you are consistent with this, then the maximum value of your tau max will always fall on this sigma 1 minus sigma 3 all over 2 equation. So again, we recall from equation 2, 10.1, 10.2, and 10.7, these two equations, or sorry, these three equations, and solving for the three unknown principal directions n1, n2, and n3, we simply get these three equations here. Okay, so if you try to make use of a three equation, three unknown, which I have not done here because it's very much involved, so you will actually yield this result. And this result is actually the basis for the Mohr circle of stresses. upon which only the numerator at the right hand side is the one that is significant. So this is actually the expression that dictates an equation of the Mohr circle. So this is an equation of a circle. Okay, so the proof on that is we try to expand this numerator here and equate it to 0. So this is now a simple expansion of this two binomial expression. Okay, and then by doing a sort of a completing square method, we simply add a value here. Okay, so this value is actually uh, the 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 completing expression that will complete the square of these three expressions here. Okay, so if we add something on the left side, we need to add uh, the same thing on the other side. Okay, so this is just to complete the square. Okay, so we still have a value here. Okay, still have a value here that is needed for us to be able to come up with a squared term here. Okay, so this is a minus sigma 2 plus sigma 3 multiplied by sigma n. Value. Okay, so this will represent now the middle term of the squared. So this is the squared term here. This is the perfect squared term here, no? So this is now a minus. So we place here, okay, this value here was placed on the other side for this to be a pure perfect square. Okay, with of course there's a tau there. The tau squared there is independent with this. Okay, so this is now a, a, a perfect square. Okay, so since if I add 1/2 and 1/2, this becomes 1 whole there. Okay, so this is a p over 2. Yes, so I think that's correct, no? So this represents now actually a form of an equation which is a simple x squared plus y squared. So if I have here an axis converted into a sigma tau axis. So this is my x, this is my x-axis, this is my y-axis. So this is x squared plus y squared. So the right-hand side must be related to a radius of a circle. Okay, so this must be a radius of a circle. So how do we convert that into a radius? So we know that the radius simply is equivalent to half of the diameter, no? So if we will try to take the square of this, expand it, and then we subtract the sigma 2 sigma 3 term, which is 2 over 4, this becomes 1/2 minus, so what will prevail is a negative sign here in terms of 1/2. So this 1/2 minus 1 whole is a negative 1/2 there. Okay, so and then we put it back into a perfect square again to yield this as your radius square. Okay, and take note that the radius actually defines again your tau. Okay, so whatever is the radius, this is represented by tau. If the radius is a maximum radius, then this is also a uh, a maximum shear stress. Okay, so this now makes you the a perfect equation of a circle that justifies the use of Mohr circle as a representation of a three-dimensional physical state of stress. So similarly for the other numerators here above, okay, these two numerators, what we will do is we only need to change, okay, some of the sigmas depending on the definition of the circle that we are going to represent. Uh, okay, excuse me. Okay, so for the other two equations, okay, you take note that if I have here an equation in terms of a sigma 2 and sigma 3, I am actually referring to my first Mohr circle, C1. If I refer to a value which has a sigma 3 and sigma 1, I'm referring to my second circle, C2. And if I'm referring to a sigma 1, sigma 2 here, I'm actually referring to my third circle, C3. So the above equations are simple equations of the Mohr circle, and the normal and shear stresses can be solved simply at any given inclination you want. Okay, so if you want to get the value of the normal and the shear stress at a certain angle of inclination, then you just refer to the circle here at a certain point upon which the angle is represented. In the physical space, it's always twice, okay, the angle of inclination. Okay, so if you have a physical state of stress given by the physical axis, say 1, 2, 3 here, okay, in which orthogonality is actually satisfied, then if we say that this is 90 degrees, 1, 2, so this 1 and 2 here has actually an angle of twice, okay, the value of the angle here. So if I have a physical rotation, a physical uh, angle describing the direction cosine, say 30 degrees, I have to plot twice, no? Twice that angle into the two-dimensional Mohr circle representation. So that is how the angle, the physical angle, the direction cosines are manifested or represented in the two-dimensional uh, Mohr circle uh, graph. Okay, so I'll stop at this point to answer your concerns or questions before we proceed with the three-dimensional interpretation of these equations so as we can apply it in a three-dimensional problem later. Thank you Thank you very much for listening, and I'll see you on the next video.